Hello, this is Jyotirmay Kantipudi. We are from Group 38, and this is my team Mohana Deepthi Karumanchi, Harshavardhan Bodipudi, and Sai Vardhan Ainavolu. The primary objective of this presentation is to showcase our language design project named Kamala. Our team has developed a comprehensive language, and we intend to provide an overview of its introduction, design process, language features, grammar, lexer, parser, interpreter, and live sample runs to illustrate its functionality. To begin with, Kamla is based on BNF grammar rule, and we've utilized Python for developing the lexer and Prolog to develop parser and interpreter, and then created flowchart that describes the functionality of the language. The source code is first provided to the lexer, which generates the tokens, and then the parser builds a parse tree with these tokens. At this stage, an intermediate code is generated, which is then passed to the interpreter to generate the output. We will elaborate on this process at a later stage. The language we've developed supports three fundamental data types, including integers, strings, and Boolean values. The integer data type can represent whole numbers, whereas string data type can store text data. The Boolean data type, on the other hand, can represent true or false values. One of the significant features of the language is its support for conditional statements using the if-else structure. The if-else structure is highly useful in creating branching logic in a program. Our language also supports two types of loops. One is for and the other is while. The for loop is useful when you want to iterate over a sequence of values, whereas while loop is used when you want to execute a block of code repeatedly until a condition is met. Our language also supports a range of operations that can perform arithmetic, logical, and comparison operators. The detailed supported features are arithmetic operations include addition, subtraction, multiplication, division. These operators can be used to perform basic mathematical operations on integers. Logical operators such as not can perform logical operations on Boolean values. Coming to the comparison operators, we have greater than, less than, and equal to, which can be used to compare values. In conclusion, the language developed supports multiple data types, conditional statements, a range of operators, and two types of loops, which makes it versatile and flexible.
The grammar of the programming language is defined using a set of production rules, which describes how the language constructs can be combined to form valid programs. The grammar consists of non-terminal, which represents categories of language constructs, and terminals, which represent the actual symbols or keywords used in the language. The highest level of the grammar is the program, which is represented by the non-terminal P. A program consists of a single block of code, which is defined by the production rule K. The block of code is defined by the production rule K. It consists of a sequence of declarations and commands enclosed in the keywords begin and end. A declaration is defined by the production rule D. It consists of multiple declarations separated by semicolons and can either declare a constant with a name, an integer, value, or declare or a variable with a name. A command is defined by the production rule C. It can consist of multiple commands separated by semicolons. The different types of commands can be used in the language are assignment, conditional, looping, block, and print. Print is usually used for outputting the value of a variable, and assignment is used to assign a variable to value to a variable. Arithmetic expression E. An arithmetic expression is defined by the production rule E. It consists of multiple arithmetic expressions separated by operators such as addition, subtraction, multiplication, and division. An arithmetic expression can also consist of an identifier or a number. Boolean expression B is defined by the production rule B. It can consist of a Boolean values such as true or false. Comparison between arithmetic expressions using operators such as equals, less than, or greater, or logical operators such as not. Identifier is defined by the production rule I. It consists of a sequence of letters and digits starting with a letter. Identifiers are used to name variables and constants in the language. Number n is defined by the production rule n. It consists of one or more digits with an optional leading zero. Numbers are used as integer values in the language. A print statement is defined by the production rule W. It consists of a keyword print followed by an identifier which represents the variable whose value should be printed.
Hey, hi, this is Harsha. I'll walk you through the code for the Lexo. So this is the code for the Lexo or tokenizer written in Python for our programming language Kamla. The Lexo takes Kamla code file as an input and tokenizes it to a list of tokens. The Lexo is implemented using regular expressions to match keywords and operators in the Kamla language. The file name variable is used to store the name for the Kamla file that is being compiled. If the program is run without any command line arguments, then a message is being printed to indicate that no file was provided. Otherwise, the first command line argument is assumed to be the file name, and it is checked to see if it has a .cmla extension. If it does not, then a message is printed, and the program exits. The file is opened using the with statement, and its contents are read using the read parenthesis method. The resulting string is passed to the tokenize method to produce a list of tokens. The tokenize function first adds spaces around each keyword in the keywords list using the replace method. Then it splits the code into list of tokens using the split method. Each token is separated by white space. The resulting list of tokens is returned. Each token is then checked to see if it is a digit or using the is digit method. If it is not a digit, then the token is enclosed with single quotes and added to the new list that we have created. Otherwise, the token is added as it is. Finally, the list of tokens is joined into a single comma separated string using the join method. And then this is how the parse tree is generated. And now my teammate Vardhan will take the discussion forward.
Hi, this is Vardhan, and I'm going to walk you through parser and interpreter. So this is the code for parser. As you can see, it's implemented in Python, in Prolog, my bad, and all the grammar rules, including program, block, declaration, command, followed by Boolean and normal expressions, along with precedence rules, as you can see here, are implemented here. We also implemented some extra rules for initializing the environment, looking up variables and updating the variables inside environment. And these two rules, identifier and numbers, are used to recognize numbers and identifiers in a programming language. Let's go through interpreter now. And this is the code for interpreter. As you can see, every tree node that's generated in the parse tree, which is the output of the parser, has an corresponding evaluation block in the interpreter. Program has its own program eval, block has its own eval block, and every other program block like declaration, command, Boolean expression, and expression2 have their own corresponding evaluation blocks. Now let's go through some of the sample runs. This first sample run emphasizes how we have implemented tabling as if it was normally passed, like where we would simply eliminate tail recursion using left recursive statements. Then this expression x minus 3 into 2 minus 2 would evaluate as -2. But instead, because we have used tabling to remove tail recursion, this would evaluate to -6, which is the right answer. In the second run, we are testing the traditional if condition. As you can see here, at first, after running the code using Python 3, just a second, let me actually run the code right here. Let's go to our source directory where all the code is. And here we call Lexer and we give the path of our code here. In this case, our test case would be our demo program. As you can see, at first, it shows us the code, followed by the parse tree, which we can call as our intermediate code for this case. And then it gives us a message saying the program is compiled, followed by a result, and then program execution is done. So this is the first test case. And let's see the second test case. Yeah, in the second test case, we are covering the case where we have implemented traditional if condition. As you can see, x is initialized to 2, and as a it's less than y, which is 10, we print 1. And this is the corresponding intermediate code for this, where things have been properly tokenized and passed down to the evaluator. Let's go for test case 3. Yeah. In the third test case, we are checking traditional while loop. In this case, we are just iterating from when x is equal to 5 to x greater than 0. And we are doing some arithmetic here. And we are printing all those answers right over here. As you can see, every other alternate line is x, which reduces from 5 all the way to 0, followed by y, which is y plus x into 2. So this is the code for that. And this is the fourth test case where we cover traditional for loops. No, this is range for loop. As you can see, we have a variable y, which is in range from 2 to 5. And we add a constant 3 to it. As you can see, it prints correctly. And now we have code for ternary if operation. So you can see here, x is 7 and it is less than 10, so we print 1. In fact, we can change the code right here. Make x 11 and run it again, and it prints 0. Next, we're going to learn 6th test case, which covers traditional for loop. So you can see here, we have a variable y, it's initialized to 2, and it goes all the way from 2 to 9. And this is the increment that it goes with, which is +1. As we can see here, we add constant 3 to it. So we get 5 to 12 as the answer, which is right. That's all for sample runs. And now let's talk about future scope. So what more can we do to this language? We can definitely add support for more data types such as double. Also, error handling and detection here is very primitive. So that's something we can definitely work on so that it recognizes more advanced errors and even hopefully runtime errors in the near future. Then we can add more control for abstractions such as functions and even structures later on. That's it. Thank you.